for having me. Yeah, so thanks, Cynthia. I'll just quickly add to that introduction that as a day job, I work as a graduate researcher in the Yale Department of Earth and Planetary Sciences, and I'm a geochemist, which means that I use kind of various types of chemical analysis to look at sedimentary rocks that come from all different ages through Earth's history. And what we try and do to get out of those is uncover kind of bits of information about the Earth's past climate, environment, anything that can help us answer kind of big questions that we have about the evolution of life and the evolution of the Earth's climate stuff and so forth. So this presentation today kind of is partly touches on things that I actually actively research, and partly it's kind of a more broad focus on climate change and what that might mean for us today. And so I want to kind of briefly introduce this by kind of touching a bit on how much more widely climate change, or the awareness of climate change as an issue that we already face, has kind of in the past few years been developed. And as luck would have it, today is the day that the new administration decided to kind of launch its new climate initiative. So I actually managed to get this clip of Joe Biden making his announcement earlier, and hopefully this is going to play. There we go. Let's see what he has to say earlier.
In my view, we've already waited too long to deal with this climate crisis. We can't wait any longer. We see it with our own eyes, we feel it, we know it in our bones. And it's time to act. And I might note parenthetically, if you notice, the attitude of the American people toward greater impetus on focusing on climate change and doing something about it has increased across the board, Democrat, Republican, Independent. That's why I'm signing today an executive order to supercharge our administration's ambitious plan to confront the existential threat of climate change. It is an existential threat.
So I think it's a really interesting change of tone kind of in the last few years, that a president is elected in this country who, as kind of one of his four, he touched a lot in his election campaign about the four crises facing America today, and one of those was climate change. And actually, I don't think it was limited to Joe Biden. In fact, despite kind of whatever he might have said in the past about climate change, Donald Trump, when he was asked specifically in the first presidential debate in September whether to what extent he thought that greenhouse gas emissions by humans were contributing to climate change, Donald Trump actually said that he believed they did. So I think the tone in America and across the world, really, when talking about climate change, has really changed over the past few years, with the acknowledgement that the climate is changing and that it presents a threat to humanity. And of course, partly this is because we can, as Joe Biden says, see it with our own eyes now. So one of the major kind of events that has happened in the past few years to sharpen people's minds, to focus people on climate change, is that we've seen massive wildfires on a scale that we've not really seen before, ever, in kind of well, at least in like recent human history. In California, in Australia, in large parts of Northern Europe and Siberia. And this is kind of one symptom of all sorts of snapshots of climate change that we're seeing across the world. This includes droughts, heat waves, but also very noticeably the melting of ice sheets. Both the Greenland ice sheet and the Antarctic ice sheet are carving, big icebergs are kind of carving off the side of these ice sheets, and we can measure the extent of these ice sheets, and we see that they're reducing in size quite drastically. And ice melting isn't just affecting the North and South poles. We see glaciers retreating at a rate that we haven't really seen before in human history so far. And And there are all sorts of other phenomenons that are going on. So this, for example, is methane or methane, as you would say here, bubbling up from having previously been stored in permafrost underneath lakes in the Arctic. And on a similar vein, these weird kind of pock marks that you see here in this photo are from Siberia, and these are craters, lakes forming in these big holes that are formed when methane gets released from the permafrost and essentially explodes. It blows up this big crater in what used to be the permafrost and the tundra. And we also obviously see this ice melting reflected in sea level rise. And this actually is a community in Louisiana called Ile de Saint Jean. And this is probably one of the first communities of climate change refugees that we see in the world. So this community was evacuated in 2016 because rising sea level in the Gulf of Mexico cut them off from the rest of Louisiana. And sea level rise is something that we actually also see closer to home, but this is in Connecticut at least seen during storm surges, and hurricanes have become at least kind of arbitrarily to us seemingly stronger and more frequent. Whether this is actually tied to climate change is still an area of open research, but it's no doubt that with rising sea levels, hurricanes have the potential to cause greater extensive flooding, as we saw in Connecticut, for example, in 2012 when Hurricane Sandy hit the coast here. And then finally, we also see the effects of climate change in the biology and life around us. So the fish stocks that we depend on for food have been changing. The range of some fish that are adapted to living in warmer waters has changed. They've moved further northwards in the northern hemisphere. Fish stocks have declined. That's because they don't have enough oxygen to breathe as sea temperatures rise. We see this effect called coral bleaching, where corals which are organisms that support a huge variety of life in the oceans, as sea temperatures rise, they become unable to sustain themselves, and they lose the pigment that enables them to create food for themselves, and this is called bleaching. And finally, and probably most distressingly, we see all sorts of animals like polar bears, for example, really struggling to survive because their habitats are shrinking as sea ice retreats. Their normal food sources are running out also as sea ice retreats. And so we'll probably see a great deal of animals like polar bears go extinct over the next few decades as temperatures continue to rise. And so we see tons and tons of evidence from the world around us of a changing climate. Although what I would stress is that all of these are very much snapshots. So they tell us at an instant what's going on in the world around us. So a forest fire, for example, is a single event. We can look at the record of forest fires like through history. And really what we mean by changing climate is that the average of all of these measures is changing. And so to really understand climate change, we need to have, an average measure to kind of measure against. And so one of the best things we can measure against is temperature. So here in this plot, what you see is the record of temperature, measured temperature, that has been taken for each month, for each year. And what you see on the y-axis, this vertical axis here, is the difference in the average temperature for each month to the average temperature for each year. So for example, January obviously is always colder than the average for each year. Sorry, the average, not the average for each year, the average across all of the years measured here, which is 1980 to 2015. What you see is that winter months obviously are always colder. This is in the northern hemisphere. summer months are always slightly warmer than the average. But what you can see is that the lines which go from purple being the oldest to red being the youngest, the lines are slowly increasing with a bit of variation, but the general trend is to warmer temperatures. Another slightly different plot illustrating this is this kind of circle plot here. Again, the months of the year are around the sides. And here we see temperature increases towards the rim of the circle. And as you see, again, with every passing year, the circle of temperature widens and widens. And then finally, there's one other plot I think that demonstrates this quite nicely, and that's sorry, I forgot. There's another. This is Arctic sea ice volume. So this is another way of kind of measuring climate state, looking at the mean coverage of Arctic sea ice, and you see this is the opposite trend to temperature. The Arctic sea ice volume has gotten smaller and smaller, and then this finally is probably quite a well-known image. You might have seen this before. Each vertical stripe here represents a single year, and the color of the stripe is representative of the average temperature in that year related to the average temperature across all the years plotted here. So bang on average would be a white stripe, such as here. A year that was colder than the average is a blue stripe, and a year that is warmer than the average is a red stripe. And as you can see, there's a trend from colder temperatures to warmer temperatures that's very obvious across here. So I'd say we have a pretty good records, and you might say an undisputable record that temperature is increasing in our lifetimes and kind of across the last 200 years. Ice volume is decreasing. The climate is changing. So that begs a few major questions. And in this talk, I'll try and kind of answer three main questions, talk about three main themes, and relate each to the others. So first, what is causing climate change today? And you might think this is obvious. Humans are causing climate change, but I'll go into a few of the reasons why we can actually know that for certain. And because there are still kind of, even though it's the debate has moved on in the past 20 years from this question, there are still people who see it differently or have a different perspective on this, and that's something that we should kind of address. Then something that is very relevant to what I study: how can we detect climate change in the past? I'll go into some of the techniques we use there. And then finally, I'll run through a bit of a breakneck tour of the last 500 million years in climate. And really, this is because to understand climate change in the future, we really have to know what has happened in the past. And really, the question is whether the time that we're living through right now is massively different to what happened in the past before humans intervened in the climate. And what that can teach us about where we might be heading in the future. And like I said, feel free to interrupt with any questions you might have. Otherwise, I'll just keep wittering on for about an hour. And then, but we'll definitely have time at the end for questions if you want that. Okay, so what is causing climate change today? Well, I'll start off like this. In the 1950s, a scientist called Charles Keeling, who was working in California at the time, developed a measurement tool which used infrared radiation to detect carbon dioxide concentrations in the atmosphere. And he started doing his measurements, and he realized that he was seeing a trend in his data. And so he fixed a measurement station in his lab where he was working in California. And this then got taken up by NOAA, the Oceanographic and Atmospheric Institute, and they carried on this research. And so we have a pretty a pretty consistent picture of carbon dioxide concentrations in the atmosphere through time since the 1950s. And what they show is this pattern. This is the same kind of spiral diagram as we saw earlier for temperature. And lo and behold, the pattern that we see for carbon dioxide mimics almost exactly the pattern for temperature. Now, now this is something we call correlation, right? When two variables, two measurements, two different things are doing exactly the same thing at the same time. We don't know whether one is causing the other, but we do know that carbon dioxide, it has a really specific property, which is that when you subject it to radiation, it absorbs radiation and heats up air. And that's something that was known since the 19th century. And we'll come back to that in a second. But this is kind of clear evidence that the concentration of carbon dioxide in the atmosphere is going up, which means that the amount of carbon dioxide in the atmosphere total must also be going up. So where is this carbon dioxide coming from? There's a few ways we can answer that question. Number one is by comparing what we do. So this is a plot that shows the total amount of carbon that we emit as humans, and this is principally by burning fossil fuels. And so again, on the x-axis at the bottom, you see the years from 1900 to 2000, and here you see this is in million metric tons how much carbon we emit. And the trend is broadly positive. It follows very, very closely the trend of carbon dioxide concentrations in the atmosphere, which I'll show you again in a minute. This is one way. So if we link how much carbon we're putting out into the atmosphere to how much carbon dioxide there is in the atmosphere, that should be quite a clear link, right, to a causation that we can say one causes the other. There are a few other ways that we can tell that the carbon dioxide in the atmosphere comes from fossil fuels, though. One is by considering how fossil fuels are, or what makes fossil fuels in the first place, how they form. So fossil fuels are, as the name suggests, the fossilized remains of plants that were buried and turned into rock millions and millions of years ago. In the case of coal, for example, this is wooded plants, so land plants like trees. They then die, get buried in sediment, and over millions and millions of years of heating and compaction, they get turned to rock. And this rock is really energy rich. It's a great fuel. The process is the same for oil and gas, except the plants are sea creatures and tiny plankton and algae. And originally, the source, the source of fuel, right, is molecules that contain carbon. But carbon is something that has to be sourced by the plants, and in fact, the carbon comes from the atmosphere when plants take in carbon dioxide from the atmosphere to grow when they photosynthesize. Now we can pinpoint exactly or we can pinpoint the carbon in the atmosphere to the carbon in fossil fuels because there is more than one kind of carbon floating around in the atmosphere. There's this heavy carbon, carbon-13, which is in red here, and light carbon, carbon-12. And these are what's called isotopes. So they are the same element, the same chemical element, but with different mass, different weight. So remember, two different kinds of carbon. One is heavier, this is the red one, and one is lighter, the orange one. For plants, it's easier to take up light carbon, carbon-12, when they're photosynthesizing. It costs them less. So plants are enriched in carbon-12, in light carbon. Now remember, the process to form fossil fuels from plants is that plants die, decay, and then get progressively compressed, heated, it turns them into rock. The carbon stays the same, which means that fossil fuels are also enriched in light carbon. So the carbon in fossil fuels is lighter. Now, what we can do is we can measure the amount of light carbon versus the amount of heavy carbon in carbon dioxide in the atmosphere. And what we get is this plot. So again, on the bottom, this is through time. This is getting progressively younger to the right, more recent. This blue line here represents the total carbon dioxide concentration in the atmosphere. This is the same as we saw on that spiral plot right at the very start. And this red pattern here means the total amount of heavy, or the ratio of heavy carbon-13 versus the light carbon-12. That's what this Greek letter delta here, and delta 13 CO2 stands for. So what this means, this trend of decreasing delta 13C means that carbon in the Earth's atmosphere is getting lighter at the same time as the total concentration of carbon dioxide is increasing. So what this means is that this additional carbon dioxide must be enriched in lighter carbon, which is the fingerprint of fossil fuels. By the way, you might be wondering why there's such a zigzag pattern on here. And that's actually because the station is in the northern hemisphere, and the peaks correspond to the northern hemisphere winter, when plants take up less carbon dioxide, because a lot of plants in the northern hemisphere have lost their leaves, and in the summer they're able to take up more carbon dioxide, so there's a big decline. So the fact that we see these corresponding trends is a really good indicator that the carbon dioxide that we have in our atmosphere is because it is derived from fossil fuels. But then actually, finally, and this is probably the most kind of obvious clue to where this carbon dioxide in the atmosphere has come from, is that these days we have such good carbon dioxide measurements that we can model on a yearly basis where carbon dioxide in the atmosphere goes. And we can come up with a graphic like this. And this is from NASA.
Hi.
Just going to mute him. And you can see the red is high concentrations of carbon dioxide. And you can see that they actually come from these specific centers. So this is obviously in the US and across North America. This is Los Angeles here. Central Europe, or or Western Europe, and East Asia and China. And what do these correspond to? Well, they correspond to population centers. So where humans are most common, are most concentrated, that's where most of the carbon dioxide in our atmosphere comes from. So I'm going to pause that there. But these three pieces of evidence, so the correlation between carbon dioxide concentration in the atmosphere and the carbon we emit as fossil fuels, the isotope signature, the light carbon signature of carbon dioxide in the atmosphere, and the actual observed pattern of where carbon dioxide comes from, all suggest that it's humans burning fossil fuels that is contributing to the carbon dioxide in the atmosphere. So the next, I guess the next point to make is that fossil fuel burning isn't actually the only thing that contributes to putting in carbon dioxide into the atmosphere. And does anyone want to take a guess at what connects all of these images? So audience participation here. I'll give you a hint. It's where we are. They're actually, all of these images are from Connecticut. So this is the R95 just outside New Haven. This is the Arethusa Dairy Farm. This is a woodland near Hampton, I think, and this is a cement plant in Bridgeport. And they illustrate essentially the 4 human activities that produce the most carbon dioxide emission. Obviously, you'd expect kind of transport, burning of fossil fuels to be a big contributor, but actually animals, farm animals, especially cows, but other animals as well, produce an extraordinary amount of methane emissions through their digestive processes. And they actually contribute like a significant proportion of our greenhouse gas emissions. Similarly, production of cement and concrete is actually a chemical process that one of its key products is carbon dioxide, and actually it contributes a sizable quantity as well of carbon dioxide to the atmosphere, similar in kind of level to different types of transportation. And actually, logging or deforestation is also a very serious contributor of carbon dioxide, because by removing the ability of the earth to naturally take in carbon dioxide, which is what plants do, we effectively increase the level of carbon dioxide in the atmosphere. So it's important to also note that not all of the carbon dioxide that we emit goes straight into the atmosphere, or if it does get recycled through the Earth system as well. So this is maybe slightly complicated figure, but all I want you to take away from that is that there are different sinks of carbon dioxide, right? There's a big sink in the atmosphere, there's a big sink in the ocean, and then also on land. So the carbon dioxide that we measure in the atmosphere isn't all of the carbon dioxides that we have emitted, because we also have really increased the amount of carbon dioxide in the ocean, because we've burned so much fossil fuels, we've emitted so much carbon dioxide. But it is the carbon dioxide in the atmosphere that's really the key to understanding climate change, and that's because of the greenhouse effect. And like I alluded to earlier, carbon dioxide is a really effective gas at absorbing heat energy that actually originally comes from the sun, but then is re-radiated by the earth and is trapped in this kind of greenhouse bubble in the atmosphere around the earth. And that's why more carbon dioxide in the atmosphere means that the earth's surface heats up. Now, one interesting thing to note is that carbon dioxide obviously isn't the only greenhouse gas. In fact, it's not even the most potent, and it's not the most abundant. In fact, the most abundant greenhouse gas in the atmosphere is water vapor. Now, if water vapor is more abundant than carbon dioxide in the atmosphere, why are we not worried about water vapor? Why are we always talking about carbon dioxide? Well, you can think of it a bit like a bobsled team, if this plays. in a bobsled team, there are a few different roles, right? There's 4 people who are the team. You'll see in a minute, there's one guy who stands at the front, they're the driver. But then there's 3 who push from the back, and they're really the legs of the operation. They give the big shunt at the start, and they really get the bobsled going. But it's the driver that dictates where the bobsled goes. And in this situation, you can think of CO2 as the driver and water vapor as doing the shunting. CO2, because it provides that initial kick to increase temperature, CO2 is what increases the amount of water vapor in the atmosphere, because as you can expect from, like, if you've boiled a pan of water, the higher the temperature, the more water vapor you're going to get. It's a bit of a shame that this video isn't playing, but you I guess you've all seen a bobsled before. You know the idea. I'll skip on. So other greenhouse gases are also show this trend of positive increase, and this is also because of human emissions. but they're not as important as carbon dioxide because their concentrations are so much lower. You can see here they're in parts per billion on this scale rather than parts per million, which is what we measure CO2 in. So other things besides human causes can also cause carbon dioxide levels to change. So we saw this picture earlier. This is showing methane release from where it's stored underground. So one possible cause of carbon dioxide levels or carbon levels in the atmosphere to go up is by initially increasing temperature sufficiently that you then free up all of this trapped methane that then also bubbles out and enters the atmosphere. But obviously that requires kind of initial warming to get that going as well. Another source of carbon dioxide actually is volcanoes, and it's quite a significant source, although the amount of human CO2 emission is like many times more than the annual kind of emission of volcanic CO2 on average. Forest fires actually also emit a lot of CO2 because burning woods, as you can expect, produces CO2. And carbon dioxide levels can also change in the other way. So blooms of plankton, of algae, or just growth of plants can draw down CO2 from the atmosphere. And then potentially something that many people might not know is that one of the other major drawdowns of CO2 is from a process called weathering, which is essentially when rocks get dissolved and chemical reactions occur to erode rocks essentially. And this is because there are chemical reactions occurring all the time here between the minerals in the rocks, the water, and the CO2 in the atmosphere. And this locks up loads of carbon dioxide and sediment. So this is one of the major drawdowns of CO2 as well. So these are all natural processes that affect how much carbon dioxide we have in the atmosphere. And make a note in your head of all of these photos because we'll be coming back to them. And then there are other ways that global temperatures can change that aren't directly related to CO2. So volcanoes, for example, also emit little particles called aerosols. And these aerosols can actually block the sun's rays from coming into the earth rather than like absorbing the re-radiated heat. So they actually reduce the Earth's temperature because they make more sunlight reflect out. The sun also plays a really big other part because the orbit of the Earth isn't always the same. So this is kind of showing a little picture of the Earth kind of in relation to the sun. And you might think that the Earth kind of travels at kind of quite a normal standard ring around the sun, but actually the position of the Earth in relation to the sun is always changing, both in the shape of the orbit, which gets more oblique and less oblique, and this happens over cycles of about 100,000 years. There's also a cycle in the tilt of the Earth. So you might know that the true North Pole and the magnetic North Pole aren't in the same place, and that's because relative to the axis, the Earth moves in its tilt, and this is again over timescales that are much longer than we will experience, but this happens over 40,000 years or so. And then finally, the Earth also wobbles around its axis, a bit like a spinning top, you can imagine. So these changes in the Earth's orbit make a real difference because it dictates how far the surface of the Earth is away from the sun. Obviously, the closer the surface of the Earth is to the sun, the warmer it will be. The more of the sun's radiation will get to us. And then there's also the case that the sun doesn't radiate heat on a consistent basis. So the sun goes through cycles where it's much stronger than otherwise, and these are kind of colloquially called sunspot cycles. So when you see loads of sunspots on the sun, that's when the sun is going through phases of kind of more strong activity, more strong burning, and that can produce more heat and it gets hotter. And then one other thing is that the surface, the characteristics of the surface of the Earth also matter, because as you might know, if you've been to the desert in the southern US or in Mexico or even in southern Europe, lighter colors reflect the sun's radiation a lot more than darker colors. So houses, for example, in desert areas are often painted white so that they don't heat up as much because they don't absorb a lot of the sun's radiation. And clouds and ice are two of the best surfaces for reflecting the sun's light. And so the more clouds there are and the more ice cover there are, the more the Earth can reflect back the sun's radiation and cool down. So another 4 images to bear in mind are these ones. There's a lot of different ways in which global temperatures are affected, basically. So drawing all of these lines together, can we conclusively say what is causing temperatures to change at the moment? Yes, we can. So this little video, and I really hope this is going to play. There we go. This little video is going to show you, first of all, the observed trends in global temperature as we see from 1880 to the modern day. And as you can see, as we saw earlier, it broadly follows an increase in temperature. And then we're going to see a series of lines that are the projections. So like if only one thing was controlling global temperature, the effect that would have. So the first is orbital changes, like we saw the obliquity of the Earth's orbit around the sun. And as you can see, that has almost no effect on increasing or decreasing temperature over this time. Solar cycles, that's sunspot cycles, also almost completely flat, has very little effect. This is volcanoes, so this is plotting CO2 emissions from volcanoes over time. And as you can see, there's a bit of variation there. That's because volcanoes come along in leaps and bounds, but overall, there's not a directional trend in temperature. And this is plotting all of the combination of those 3 things together. You'll be able to see, there we go, natural factors. That's all 3 of those plotted together. And you can see there's variation in temperature, but there's not a directional increase in temperature for those. So then we come to human or human-related factors. So land use, actually, you'd think deforestation would cause an increase in temperature, but actually land use over the last 200 years hasn't really affected things that much. Ozone is one thing we haven't discussed, but this is basically also a layer in the Earth's atmosphere that acts to block out the sun. So by reducing the ozone layer, we actually have slightly contributed to warming, although not to a significant extent. Aerosols shows a really interesting trend. That shows a real cooling effect. That's because we ourselves have put loads of aerosols into the atmosphere. But what is very, very clear is that greenhouse gases are the major factor in contributing to the observed trend in temperatures over the last 200 years. And you can see that this is all of the human-related changes plotted together, and then this is the single line representing all of those 4, and it matches the observation reasonably well. So what is causing climate change today? I hope I've been able to convince you that we have a lot of evidence to suggest that it's greenhouse gases, and specifically greenhouse gases emitted by humans. So now, because we're we're quite a lot over halfway through, let's move on to the last kind of 2 sections, and this is where it gets quite interesting. So all of those, when we're measuring climate, like we've discussed in the kind of the last few slides, we're reliant on determining how hot the planet is. And this involves measuring temperature directly. Now, if we're going to talk about climate change in the past, we can't do that because we have no way of measuring temperature directly. So what we need to come up with are different things that we can measure from which we're able to calculate what the temperature was and how much CO2 there was, for example, in the atmosphere. And these are called proxies. Now, sometimes, and I'm going to talk about how we detect carbon dioxide levels first. Sometimes we don't actually need proxies. So this photo is an ice core. And what it is you can see these layers. Each layer here represents a year's worth of snowfall. And I think this is an ice core from Greenland. So the this is in an area there where the snowfall is completely undisturbed. So what happens here is that each year an extra layer of snow falls on top of the older one and buries it. That eventually accumulates so much that the layers at the bottom get compressed and are turned from snow into ice. Now what that does is it traps air bubbles between the little snowflakes at the top, and it forms these air bubbles deep inside the ice. And we can actually tap into those air bubbles and sample them directly. So we have a record of the atmosphere from these ice cores, and the age of these is quite staggering. And we can count the layers to determine how old some of these ice cores are. And we actually have direct measurements of the Earth's atmosphere from up to 800,000 years ago from these ice cores, which is pretty incredible. But sadly, if we want to discuss, if we want to look at measurements of the Earth's atmosphere from older than 800,000 years ago, we can't use this technique. What we can use is these holes on the surface of leaves, which are called stomata. Now, these holes are what the leaf or the plant uses to breathe in, essentially, carbon dioxide from the atmosphere. Remember, plants need carbon dioxide in order to photosynthesize. So the size and the density of these holes on the surface of the leaves reflect exactly how concentrated carbon dioxide is in the atmosphere. Because the more concentrated carbon dioxide is, the fewer of these holes the plants need. Because the holes in the leaves are actually quite bad for the plant because it loses quite a lot of water out of them. So it will only have as many holes as it needs, not more. And then we have all sorts of other chemical ways of telling how much carbon dioxide there was in the atmosphere. And again, this comes from the isotopes of these elements, like we discussed earlier. I'm not going to go into the details of that because it's quite complicated and not very interesting, but we can use records of these chemical isotopes from fossils. So this is a sea fossil called a foram, or from whole sedimentary rocks. And we can do this from sea creatures, but we can also do this from soils. So these are rocks that are essentially really old soil horizons. And this is another type of fossil that we'll come back to in a minute. But essentially, we have a reasonably good record from all of these different proxies of how much carbon dioxide there was in the Earth's atmosphere in the past. And then I'm quickly going to also talk about temperature. And temperature is a slightly more difficult thing to get at. But in a very similar way to for carbon dioxide, we can use isotopes of different elements. So remember the process we talked about when we were talking about plants taking in carbon dioxide from the atmosphere? Well, almost the reverse process of this in a kind of, well, not the reverse, in a different way, a process that occurs in the global ocean is evaporation of water. Now, similarly to carbon isotopes, there are different kinds of oxygen isotopes. So again, we have heavy oxygen, which is in purple here, oxygen 18. and we have light oxygen, oxygen 16, which is in pink here. Now, for evaporation, again, it takes more energy to convert water. These oxygen, this oxygen base, by the way, is in water molecules, because remember, water is H2O. So there are two. There's one oxygen atom in each water molecule. Now, it's energetically, it costs less energy to make lighter water, so water with pink light oxygen, into water vapor, which means that in the atmosphere there is a lot more light oxygen than there is heavy oxygen. But again, when it gets hotter, the ratio of light to heavy oxygen will change. And obviously, the oxygen that's in the atmosphere is the oxygen that will then get rained out as rain, and that will eventually reach its way into ice. So the amount of oxygen in ice cores we can use to reconstruct temperature, or the amount of light and heavy oxygen. And again, like for carbon dioxide measurements, we can use fossils to determine this as well. There are also different measurements, different proxies that we can use for detecting temperature in the past that I won't go into in much detail, but they are from these chemical molecules in different fossils. And I'm not going to go into those, but suffice it to say that we have a whole suite of different proxies that we can use to detect how warm the Earth's temperature, the Earth's surface was in the past. And so, armed with those tools, we can go on our tour of the last part of this talk of the last 500 million years in climate. Now, I'm just going to draw your attention to this plot, because we're going to use this plot to kind of, well, as a map on our tour almost. Along the bottom here, we have time. So on the very right is where we are now. So this is the present day. Notice that the scale changes at each step. So in the first kind of few increments, going from right to left, we're going in 5,000 year blocks. But then we change up into 200,000 year blocks. So there's a lot more time in the second step here than there is in the first step here. And then we jump up into blocks of 1 million years, then into 10 million years, and then into 100 million years. So as we go from right to left, not only are we going back through time, we're also extending the time we capture in each block. That's one thing to note. And then on the on the y-axis, the vertical axis, we have average temperature, versus compared to the modern. So on the right here, you see that in degrees Fahrenheit. On the left here, you see that in degrees Celsius. And the time we're gonna make it a bit easier to tell the time by thinking of the history of the Earth as a calendar year. So the Earth is about 4.5 billion years old. So across so think of the birth of the Earth, if you want to call it that, the origin of the Earth as midnight, the first second of the new year on January 1st, and then where we are now is midnight on December 31st, almost a year later. And our last 500 million years of the Earth's history, if the whole year is 4.5 billion years old, our last 500 million years starts on the 21st of November. So we're actually only looking at a very short interval of Earth's history. But that's just as a rough guide. So our first kind of jump back through time is going to be to 1,000 years ago. And 1,000 years in the year of the Earth's history is really not very far at all. So we're actually still on the 31st of December, and we're actually only 7 seconds before midnight. That's how short 1,000 years is in the grand scheme of the Earth's year. But it's important to note that the last 1,000 years has actually seen quite a lot of variation in the climate. So we think of climate change as like, or you might think of climate change as a modern phenomenon in the past 200 years from what we've talked about previously. But this is a photo, or this is a painting rather, by Bruegel, who's a Dutch painter who painted a lot of these scenes, which show frost fairs. Basically, the surface of rivers and lakes in Central Europe froze over almost completely every year in the Middle Ages, and actually this is, I think, from the 17th century, to the extent that people used to congregate outside on them. And this doesn't happen anymore. And in fact, it didn't happen even 100 years ago, really. So this shows that at that point, temperatures were much colder on average. Going back a bit further, though, we know that there were extensive settlements, for example, on Greenland, which was described as quite a nice place to live by the early settlers about 1,000 years ago. So as well as there being colder periods a few hundred years ago, there were also warmer periods a few hundred years before that. And this fits in quite well to our understanding of solar cycles. So in the last 1,000 years, the major thing driving warming and cooling phases were whether the sun intensified or decreased its radiation. And on top of that, we actually can pick out individual volcanoes, for example, Krakatoa in the late 19th century, as having the effect of cooling the planet, for example, for a period of a year or two. So over this timescale, it's these two factors that are the most important in driving climate variation in the Earth. Let's take another step further. And we're looking at the last 10,000 years now. In fact, we're still on the 31st of December, and we've not even made it more than a minute, or just over a minute, back from midnight. So we're now we're only a minute and 10 seconds into the year. But the timescale of change has increased quite a lot now. So now we have almost the entirety of recorded human history in our steppe. So this is the ruins of an ancient civilization in Ur in Mesopotamia. So this is in the Middle East. This is where the first kind of major cities are found. And and you can see that today it's quite an arid region. When this was the cradle of civilization, it was much more or agriculture was much more easy to farm here. So that should tell us for a start that there has been some major climate change over that period of time. Looking at our best data for this time period, we see that actually the climate hasn't changed an awful lot. You can see these little vertical variations. Those are what we saw earlier, the 100-year timescale variations in volcanoes and in sunspot cycles that give this kind of slight kind of jagged edge to these lines. But you can see that over 10,000 years, actually, the average temperature remained fairly stable. And if there were any variations, actually what drives variations over 10,000 year timescales is orbital cycles, like we saw. Let's take this one step further, because we'll discuss this in slightly more detail, and jump to the last 1 million years in climate. Any guesses as to what date we're on now? I think you're muted, Cynthia. Oh, okay.
The 30th? Do you hear me?
Yeah, I hear you.
Yeah.
We're actually still on the 31st. We're really not going very far at all. we're actually still at 10 o'clock at night, so we're only 2 hours before
Oh,
midnight.
wow.
We're really going at a snail's pace, but I
Oh,
think it's worth it. Um, this is Connecticut a million years ago. We are sat at the moment under a huge ice sheet that is stretching a few hundred meters probably above our heads. Um, but at the same time, over the last million years, this was also Connecticut. So we have evidence of fossil animals, for example, that lived at kind of roughly the latitude that we are now, that today are found in tropical and subtropical areas. And yet we also have evidence for an ice age. So we know that over the last million years, climate has varied sufficiently to give us hotter conditions than we are at now, and also colder conditions. And looking at our map, our graph here, we can see that variation. You can see this pattern of jagged spikes here. And notice that the time scale on the x-axis here is so long now that all of what we've discussed here would fit into just one or two of these vertical spikes here. So we're talking over much, much longer timescales than we were earlier. So what can explain these variations? Well, we've just touched on them. This is, um, I should say these are things that have also been invoked to explain kind of temperature change. So methane release from ice, the reflectance of like an ice-covered surface, and also a role for biology in the oceans. But ultimately, the driver of these variations during the ice ages was orbital cycles, and we know this quite well because of mathematical models that we use. And actually, evidence for these cycles over 100,000 year timescales and over million year timescales aren't just in the last million years, but we can also find them from these rocks that were formed 200 million years ago in the Jurassic, so while the dinosaurs were around. So fluctuation in climate over timescales of 10 to 100,000 years is something that we see throughout Earth's history. So let's take another step back and go back to 60 million years ago. And we're now taking a few bigger steps back now. So we're now on the 27th of December. So we're actually days back into the old year. But this is the time period when mammals evolved into the forms that we see today. So these are Australopithecus. These are the ancestors of modern humans, and these were around only a few million years ago. But during the last 60 million years, our ancestors essentially evolved from small shrew-like animals to all the way to us. So it's a really, really significant period of time. But in climate terms, potentially, it's even more significant. Looking at the curve, we see all of these kind of vertical little squiggles here are the same kind of cycles, ice age cycles that we observed on the right here. But we actually see quite a significant trend of increase in temperature. And so to find out what is causing this trend, we actually need to zoom out even more. And we're going to consider the whole of the last 500 million years. And this takes us back to November the 21st. And during the last 500 million years, of course, some pretty huge events in Earth's history happened. So the dinosaurs evolved, but we also had periods of time when most of the Earth, including Connecticut, was covered in desert. This is what gives us the rocks that we see in kind of around New Haven. This, like, you might know it, this kind of red sandstone. That's actually from the Triassic period, and that was formed in a desert. We had the early evolution of land animals. So these are kind of these weird arthropods and weird lizard-like things that we don't even see anymore. But we also, and this is overreaching it a bit, this is about 600 million years ago, we also had periods of time when the Earth was completely frozen. So massive, massive swings in climate. And plotting our best estimates for how this looks on our plot, we see these huge, huge variations, much bigger than we see on timescales of thousands of years, 10,000 years, even millions of years. And over such long timescales, we also see that the CO2 record, and this is using all of these different proxies that we came across earlier, the CO2 record also fluctuates massively. So the amount of CO2 in the atmosphere has changed an awful amount, much more than the change that we see in the modern day. And that's because of these processes. Now remember, weathering and volcanoes really make a tiny, tiny, tiny impact on short timescales, but on geological timeframes, over millions and millions of years, they can contribute to really significant changes in the amount of CO2 in the atmosphere. And that's what causes these long-term warming and cooling trends. As does the fact that the sun actually has become slowly hotter over time, which is also a significant factor. So what we see is that over the last 500 million years, what drives climate change really depends on what timescale you're willing to look at it. Over really short timescales, individual volcanic eruptions make a massive difference, and sunspot cycles do. Over slightly longer timescales, it's the Earth's orbit around the sun that dictates if it gets warmer or cooler, and that's what caused the ice ages. And over even longer timescales, over millions of years, it's carbon dioxide levels in the atmosphere that relate to really, really slow chemical weathering of rocks and volcanic output. So, on the last kind of point that I'm going to talk about, and that will be nicely kind of an hour talk, is this question: can we use the last 500 million years of Earth's climate history to learn anything about our future? And bear in mind that we live in a period of time that is pretty unheard of, or at least we don't have many good analogies for it, because there is really, really rapid warming and a lot of really rapid carbon dioxide emission into the atmosphere over a time scale that is much, much shorter than anything that we've dealt with over the Earth's history. But actually, it turns out there might be one event, or there might be a few events, but one event in particular that might be quite a good match. And that's the snazzily names Paleocene-Eocene thermal maximum. Now, this was an event that happened in our calendar of the Earth's history on the 28th of December, so about 55 million years ago. And it actually corresponds to this peak here. You see on the green line, this kind of vertical spike in temperature. And you can see the Earth was a lot hotter than it is today during this time. But essentially, this is a time that, as well as seeing this trends, we see lots of other changes happening on the Earth's surface. So we see these massive spikes in oxygen and carbon isotopes. So this indicates that there was a huge release of carbon dioxide into the atmosphere, and at the same time, a massive sharp warming, similar to what we see today. And at the same time, the composition of plants on the Earth's surface drastically changed. There was widespread aridity. We have good evidence for deserts becoming much more widespread, and plants becoming more widespread that liked drier climates. We also have, interestingly, evidence that there was dwarfism in many more animal species than there was before. And we also have evidence that ocean circulation radically changed. We also have extinctions going on at this interval. So this is, we saw this earlier, this is a foran fossil. and a lot of these went extinct at the Paleocene-Eocene thermal maximum. So there are a few things that have been invoked as causes for this, and they include widespread forest fires, widespread methane release from ice, and really active volcanism. But remember that's we need to have a mechanism by which we release loads and loads of carbon into the atmosphere at really short timescales. So it's actually really not easy to explain this, but these are some of the theories that have been proposed. Now, I'm going to finally talk about how we can use this information to understand how climate works, but also carrying it forwards to comparing it to our present day situation. And we do this using climate models. So models are mathematical formulations, essentially, of the Earth's climate system. I quite like this quote here. Models are not right or wrong, they're always wrong. They're always approximations. The question you have to ask is whether a model tells you more information than you would have had otherwise. So a model essentially comprises of a few different parts. You put in values, there's a simulation, and then you get out results. For example, in a model of the PTM, the Paleocene-Eocene thermal maximum, we could put in how much carbon there is in the atmosphere. The simulation would then be kind of a series of reactions that would happen in the Earth's atmosphere, and the output would be the temperature. And so because we have really good records from the PTM, we can test how good our simulation is using the inputs and the outputs from the PTM. And then we can apply that to the modern, and we can test what the outputs will be. And that gives us a prediction of where we will be in the future. Now, I should say that even though the PTM is kind of the best analogy to our current state that we have, it's really not as serious as what we are undergoing through at the moment. Both because the total amount of carbon released into the atmosphere was less, and also because it was spaced out over such a long period of time compared to the modern day. So the grey is how much carbon we're putting out into the modern day all at once. The orange is how much carbon dioxide was put into the atmosphere during the PTM. So you can see that what we're doing to the atmosphere today is much more extreme than even the most extreme event we have in the geological record. And that's something that's pretty profound to realize. But what is a good outcome of this is that actually our model results of the modern day match pretty well what we're forecasting. So this is kind of superimposed the observations that we have and the best model estimates that we've had. The less good piece of news about that is that this is the forecast for the future. And you can see this is warming on the y-axis and this is time on the x-axis. And really what I want to leave you with here is that there are many different ways that this could end. And this is maybe a slightly gloomy way to end this presentation, but the really which scenario we follow really depends on what we do now, because in the extreme case where we carry on emitting the amount of carbon dioxide that we do now, we follow a path that results in warming at a scale and in a time frame that we've never seen in global history ever. And there's also scenarios where we level off our warming, and this probably will result in kind of minimal disruption. But if we do follow this most significant warming pathway, humanity will have serious issues struggling to survive the next 100 years. And we can see that in the geological record of the PTM, but also throughout geological history. And on that kind of slightly somber note, I'd like to thank you all very much for listening to me wittering on for an hour. And if you have any questions, I'd be delighted to try and answer them. Thanks.
Thank you very much, Tom. So how did they predict these lines here that you have here, the red line, the tan line, and the blue line?
Yeah, good questions. So each of these is a different level of carbon dioxide emission. So
Okay.
I don't actually remember what RCP stands for, but essentially this red line is if we I think if we carry on emitting the same amount of carbon dioxide as we are now into the future, and the blue line is if we drastically cut carbon emissions, and the other two lines are in betweens. Okay. And the calculation is essentially this mathematical model where you put in a series of values and you get out kind of a temperature prediction. And the way that happens is modeling the feedbacks of greenhouse gas concentration in the atmosphere, how much solar radiation that would reflect. So it's essentially a model of the Earth in a mathematical sense, and it's really limited in that sense. But like this plot shows, we've managed to recreate, or we've managed to predict changes reasonably well in the past based on these kind of models. Yeah.
Thanks. I see a question in the chat here. She's asking, is there a way to increase plankton? You had said this in one of the ways to draw down CO2 from the atmosphere.
Yeah, that's a really good point. So, and yeah, there is. So this touches on something called geoengineering, which is one of the ways that people have kind of thought of tackling climate change by artificially reducing the amount of carbon dioxide in our atmosphere once it's already there. And you're exactly right. Plankton, we can boost the number of the amount of plankton in the oceans, and that would draw down a lot of CO2. And one of the really good ways potentially of doing this is by fertilizing large parts of the ocean with iron. Now, why iron? Because iron is it's called a micronutrient. So it's one of the key elements that organisms need in order to grow. And it's actually the limiting nutrient in many parts of the ocean. So plankton have all of the other elements that they need to grow, such as nitrogen and phosphorus, available to them, but they're lacking in iron. So the theory is that if we add iron in parts of the ocean, then we can give the plankton all that they need to grow, and which means that they will grow. That's the theory. So it has iron fertilization experiments have been done quite extensively actually in the last 20 years. And the evidence or the results of those experiments is quite mixed. So some were quite successful, some were less successful. The I guess major drawdowns in doing this kind of on a massive scale is that it costs an incredible amount. You need to source the iron from somewhere, so you need to process rock and then draw out iron from that, which is potentially quite a costly process and potentially quite involves emitting quite a lot of carbon dioxide in the process by fueling this. Yeah, so it's definitely a great method to try and get down carbon dioxide in the atmosphere potentially, but still under research.
Interesting. Thank you. So we have another question. Did we see a drop in greenhouse emissions during the pandemic? And is this a sign on how we can make an impact if we reduce fossil fuel burning?
That's a really interesting question. And the answer is no, not at all. In fact, I think the increase in carbon dioxide in the atmosphere actually sped up during this year. And that's, I mean, there's several different reasons for that. So one is that in the grand scheme of things, the amount of carbon dioxide that we emitted didn't fall that much, even though we cut out aviation and transport for a large part of the year. And actually, one kind of reason for that might be that we actually emit loads and loads of carbon dioxide from charging stuff that we use every day. So for example, by the whole world being online the whole time and charging their devices the whole time, we're actually getting through almost as much fuels as we were by traveling and using devices less. Another thing might be that we were using more energy to heat our homes or to cool our homes in the summer, and also that large parts of the world didn't actually experience lockdown to the same extent. So in China, for example, after kind of a few months, business went on as normal pretty much, and China is the leading producer of greenhouse gases in the world. So that might also have contributed to that. But then another thing is that we briefly touched on the different sinks of carbon in the ocean atmosphere system, and it takes a few years for carbon to balance out. So it might be that if we're pumping less carbon into the atmosphere, we still don't see a massive drop in atmospheric carbon dioxide because a balance will always be maintained between the ocean carbon dioxide concentrations and the atmospheric carbon dioxide concentrations. So if we really did cut out aviation, maybe even the internet for a few years at a time, we might indeed see a drop. But over short time scales, it's probably unlikely. But it does raise a really interesting point, because obviously a lot of people had previously said, well, getting the world to cut out aviation or transport is incredibly difficult. But if we can do that, we might have a really good shot at tackling climate change. And the answer seems to be that it's a good shot, but it's probably not enough. So we need to pair both massive reductions in greenhouse gas emissions, even more than we saw during lockdown this year or last year, with measures like Sterling suggested, to actually draw down carbon dioxide from the atmosphere.
And so Sterling's following up on her question. She said, "Thank you for such a great answer. Is there any way to hasten weathering, or help it happen through geoengineering?"
So this is actually something that's very close to my heart, because it's a project that I'm working on right now. We're testing currently whether we can speed up natural weathering rates by dumping, for want of a more kind of nice image, dumping tons of crushed basalt or basalt rock onto sediments just offshore. And what we're trying to see is whether the presence of all of these minerals, these silicate minerals, in the presence of worms and kind of other biology, will speed up how quickly those silicate minerals dissolve. And in that case, it might foster kind of sped up drawdown of carbon dioxide. It's basically, I mean, if it does work, it's something whereby we'll probably have to spend billions of dollars mining and distributing large quantities of rock dust over huge areas of the ocean to actually make a significant difference. And that's probably the best way of doing it. But I guess every little helps. But yeah, it's a really interesting question, and it's actually one that I'm actively researching at the moment. So I'm glad you brought that up.
Well, thank you very much for this talk. It was very interesting. So thank you. I don't know if anyone has any other questions. We didn't manage to get live, but I do have it on recording. So but thank you so much. This is wonderful talk.
Oh, brilliant.
Very detailed, and I learned an awful lot. So thank you.
Yeah, thanks for having me.
Thank you. I don't know. Does anyone have any other questions? Okay. All right. I guess not. All right. Thanks so much. Thank you so much for tonight. And thank you to everybody who participated. So thank you again to the Peabody Museum Speakers Bureau for doing this. I really appreciate it. And so I'd love to have you back sometime, Tom.
Yeah, I'd love to come around once COVID is out of the way and done.
Yeah, that would be great to have you come and do a talk. We'd love to have you.
That'd be fab.
Yeah.
Thanks, Cynthia, for organizing.
All right. All right. Good night, everyone.
Night.
Bye-bye.